I had to really think what to talk, so I decided to talk about orthogonal polynomials, elliptic curves, and of course algebraic combinatorics or algebraic graph theory. Note here that I mentioned what is my homepage, and if you put if you extend this with these preprints and then HTML, then you'll get the preprints. Of course, they're hidden because they're not supposed to be public, but I really don't care. So we have lots of slides, but you guys gave so many definitions that I'll be able to skip a lot. I'll first start with graphs and eigenvalues. Of course, everybody here know about that, so I don't need to define adjacency matrix. Aida already talked about walks, which can be calculated from the power of adjacency matrix A to the H. So I don't need to mention that at all. What I would like to say is just that the eigenvectors and eigenvalues can be interpreted very combinatorially, so that this is labeling of the vertices, so that if you find a constant, that you can multiply every label with this constant, and that if this is equal to the sum of the labels on the neighbors, then you actually have the eigenvector and eigenvalue. Of course, provided that this vector is not all zero vector. Okay, of course, we know that what are the graphs with one eigenvalue or two eigenvalues. But the interesting inequality, which can also be derived very elementary, is that the connected graph of diameter d has at least d plus one eigenvalues. And of course, when you have an equality, then you're interested in the equality case. And the main example is, of course, distance regular graphs, which I'll introduce later. But again, I don't need to introduce that so much. But I would maybe encourage people to give to students many problems where they calculate the eigenvalues themselves. It's quite an entertaining thing. I think at one point, Paul Terwilliger said that he stopped taking other courses because he had to calculate so many eigenvalues. And yeah, that's a good way. And of course, I again don't need to talk too much about interlacing because Willem Hamers is here, and many people already mentioned interlacing, but it is one of the essential tools that I'll use as well. Okay, now orthogonal polynomials. So orthogonal polynomials, just following my supervisor's book, Chris Gottsiel, he said, well, everything depends on measure, but measure has to be chosen so that this integral of x to the n has to be finite. And then you can define the scalar product with this measure, and you can find the orthonormal basis where the nth polynomial has degree n. And this sequence of polynomials, this orthonormal basis, is called orthogonal polynomials. And of course, you can also work with finite support, and then you'll go only to the polynomials to degree m and not further. But of course, you can also go to the infinity if you want. Of course, these three people that I listed here, Chebyshev, Markov, and Stiltes, they were the one who started the field, worked heavily. I now start to follow who is coming from where, and I found out two are Russians, one is Dutch. Very interesting. I would say the last one isn't, but of course he is. Okay, so the orthogonal polynomials have this nice property that they have, there is a free term recurrence relation, and this relation actually helps us recognize these polynomials. And yeah, we can also interpret the n plus first polynomial as characteristic polynomial of this first matrix here. And this is also the matrix that is similar to another matrix that doesn't have any square roots. Now, this first matrix is symmetric, which means that this polynomial has real zeros. And this second matrix is kind of, if you change n to n plus 1 to n, you see you just get a little bit shorter matrix. And if you consider the path, weighted path, and use the interlacing, you'll kind of find the short proof that the zeros of a polynomial of n degree interlace the zeros of polynomial of n plus first degree. Okay, now Chebyshev basis. Now I have to tell you that I started my studies in mathematics in Slovenia, where function analysis was really strong, and we studied these orthogonal polynomials. And so when I left Slovenia, I thought now I'll do combinatorics. There won't be any polynomials. Oh, how wrong I was. But then again, after my PhD, I got a job at some crypto company. It was actually industrial postdoc. And I thought, okay, well, now there won't be any orthogonal polynomials anymore because I'll do cryptography. Oh, how I was wrong again. So let me start with the problem. In cryptography, you usually want to calculate the power, say, for example, alpha to the 21. And if you want to do this by alpha times alpha times alpha 21 times, this is actually exponentially slow process. Of course, exponentially slow in the length of this exponent. Of course, we want to work with 100 digits or even longer exponents, and then this would be very, very slow. What we do instead, we use this square and multiply algorithm. So here I, for example, wrote 21 in the binary basis, 16 plus 4 plus 1, so this is 21. So there is no 8 and there is no 2, so this is 10,101 in the binary basis. And I start with 1, so I take alpha, I go to the next level, 2 digits, I square. I go to the next level, I square again, but because I have 1 here, I also multiply with alpha. Then again, I have to square 2 times because I have here 0, and then I have to multiply for this last one. And yeah, this way I did only if the squarings are multiplications, and multiplications with alpha are also multiplications. I did only 6 multiplications. Alternative way is you just pre-calculate all the powers, alpha square, alpha to the 4th, to the 8th, to the 16th. And then you just look the binary representation and you multiply those which appear in this binary representation. And again, you would survive with 6 multiplications. Of course, in this small example, there seemed to be not a big difference between 6 and 21, but definitely it is when you have bigger numbers. Now the question was, can you do squaring faster than general multiplication? Because you see here, you have to square for every position you move to the right, you have to square, square, square. And if the squaring is cheaper than multiplication, then you, of course, profit. And the answer is basically no, because you can calculate the product out of 2 squares. So you see the formula, you're well aware of that. Everything cuts out all the squares, but 2ab and then plus the other 2ab, and that's 4ab, and 4 cuts out and you get ab. So yeah, maybe you can do twice faster, but not more than that, because you can express this with 2 squares. So yeah, there is no easy way, but we are actually wrong, because we were here dividing by 4, and it's not always possible to divide by 4. If you are working in finite field and your characteristic is 2, then division with 4 is not possible. And there the answer actually is that you can square much faster. And one of the possibilities to do this is to choose in the finite field, which is actually vector space over the prime field, that you choose normal basis. Normal basis is such a basis where alpha to the p, and all the way to alpha to the p to the power n minus 1, that these elements are linearly independent over. In the normal basis, when you take to the power p the basis representation and the coefficient just cycle by one place. So it's basically cyclic shift in this basis. And if you take p to be equal to 2, then squaring is just cyclic shift, and there is almost nothing faster than shift in computers. So this means that the squaring can be very, very cheap. So basically squarings are for free, and only the multiplications with alpha that we needed to do before, this is needed, this is costly to calculate the exponent, which means that we profit about, we reduce the workload for about, I don't know, to 1/3 of the previous work. Now, of course, squaring is cheap. This is fine, but now how is it with multiplication in this basis? And first, you have to figure out how to multiply any base element with alpha, and then you find out that this is just enough. Now, of course, because this is the basis, such a product is linear combination of base elements, and you get one row of the matrix for every product if you're changing m. So altogether, you get the whole matrix of these coefficients, and you would like that you have as many coefficients equal to 0 as possible. And turns out that the lower bound for that is 2n minus 1. That's kind of an easy homework, so I'll let you do it, of course, after the lecture. And now the question was, are there any bases, normal bases that reach this lower bound? And the answer was yes. These were the three authors. Unfortunately, I couldn't able to find the student Tuzichuk, who was a student of these guys. Already did most of the work. But anyway, so they proposed two constructions of normal basis, and they call them optimal normal basis if they reach this bound. Now later, when we tried to use this finite field arithmetics for elliptic curves, it turned out that there were attacks on elliptic curves if this field extension n is composite number. So one day, Scott Vanson, who was my supervisor at for postdoc, said, well, you know, you have to assume that n is prime. Well, but now this first construction assumes that also n plus 1 is prime. So there goes the type 1 basis. We couldn't use them anymore. And so the question was, can we make this type 2 basis fast? And it turns out that these type 2 bases are generated by alpha, which is gamma plus gamma 1 over gamma, where gamma is 2n plus first root of unity. Yeah, so this was my my problem. I had to somehow find fast multiplication and also inversion, which was needed in finite fields. So what I did was I called beta I gamma to the I plus gamma to the minus I, and I realized that these betas are just permuted of the normal basis that I started with. Now these indices of betas will behave like powers in some sense. So that's why we call this umbral optimal normal basis, and in short, just UB. So I had to figure out how the arithmetics will go, in particular the multiplication with basis elements. So beta 0 was, of course, 1 plus 1, so this was 0, so I didn't need to worry about that. Then I had beta k. If I squared it, I got just one element, beta to the 2k. So this is where I get this 2n minus 1, because here I get only 2 terms. Okay, and then I have a little bit of symmetry that are the second and third item. But this third one was the most important, that beta I times beta j is actually beta I plus j plus beta I minus j. And here I could put absolute value, but it doesn't matter because of this second property. And of course, this is an easy multiplication, so there is not much to do. But when I wrote this down, that this is actually what is the formula, I said, well, this is very close to polynomial basis. In polynomial basis, you have x to the I times x to the j is x to the I plus j. So there you go. These multiplications are comparable, especially if we do these multiplications using some tables. You can hide this addition in the tables, and then you have as much work as in polynomial basis. So they were comparable. And for a long time, I thought, well, these are umbral bases and so on. And then I was reading about Chebyshev polynomials again. I thought, oh no, this is actually Chebyshev recursion. So these are Chebyshev polynomials. And that's why I say orthogonal polynomials popped out again. But I needed to figure out how to do the inversion. So I defined, well, in polynomial basis, you define polynomial p of x as this linear combination of these powers x to the I. In umbral basis, you do the same thing, just instead of this x to the I, you take beta sub I, and you have to also say what is the degree of such polynomial, and this was the largest subscript, which was with non-zero coefficient. Okay, so now I needed for integers, you have that if a is larger than b, when you do Euclidean algorithm, you do a is q times b plus r, where actually this q is a over b, and then r is just calculated from this equation. So I needed something similar, and there was no problem. You would just multiply with beta with index consisting of the difference between degree of p and q, and you would cancel the first term, and the remainder would be smaller. So you could do that, what we usually do in Euclid algorithm. Okay, well, actually, where's the unity, you may ask, and it turned out that the sum of all beta i's, if you assume that they were defined by a root of unity, that's actually 1. So there I had also unity, so there was no problem. But then again, when you work with polynomial basis, you have to have also irreducible polynomial. So you have to decide what would here be a irreducible polynomial with which you are canceling. Now, irreducible polynomial, usually you take modulo of this polynomial and you consider that this is basically 0, and you calculate f n out to be this sum x to the I f I, and that's how you are doing the reduction, and you assume that this is different than 0, this coefficient. Well, actually, because I have already this relation in the second item, then I only had to prove that this sum is actually reducible polynomial, so that I cannot write it as a product of smaller polynomials. And once I did that, I actually had extended Euclidean algorithm work in this umbral basis, or if you want, Chebyshev basis. And luckily, we were now ready to do cryptography, the cryptography which used elliptic curves. And this cryptography was, this group on elliptic curves was proposed by Neil Töplitz and Victor Miller. Okay, so this was the result, and you see, you cannot run away from orthogonal polynomials. They keep coming. The challenge is just to understand them well. Okay, now the rest of the talk, I'll of course move back to usual algebraic combinatorics for this workshop. But fortunately, so many of you guys already defined association schemes, even Dean just before me, so I don't need to do that. I would need to define Bose-Einstein algebra, but again, I'm sure somebody did that as well. This follows from this axiom that the product is actually a linear combination of this symmetric 0-1 matrices that they sum to 1. And okay, so it was Ellsworth who started using this in the field of coding theory, because before this association schemes were introduced just with applications in statistics in mind by both in Nair. But yeah, it turned out that there were many more connections with group theory, linear algebra, metric and cometric spaces, which actually define the distance regular graphs and polynomial structures. And yeah, we will see that this area is fruitful because of the duality. And okay, I could mention also Bana and Ito's claim that this is a study of combinatorics objects with the theory of characters, or that we study really groups without defining a group. But there are also other connections with not theory programming, linear bound, finite geometries, and so on. So okay, so we have this product as a linear combination, which gives us the constants, structural constants that we call intersection numbers. We all know the properties of these intersection numbers. So I'll skip this part, but these intersection numbers are cardinally actually count the elements in the set, and this set is natural number or zero. So definitely we have this integrality condition on the structural constants. Now Jack already mentioned infinite families of distance regular graphs. They all actually also come from association schemes, but since we are all familiar with that, I'll skip this as well. But I'll point out that we do have the duality, because the orthogonal idempotents, the projections into eigenspaces, actually form another basis for this space that is generated by this relation, the matrices that represent relations in association scheme. Okay, and because we have another basis, then we can write everything in this other basis. So we have also two products, the ordinary product and Schur or Hadamard product. And so this way we get the new structural constants, and these are called crime parameters. For those ones, we don't have necessarily combinatorial interpretation, but we have this inequality that crime parameters are cannot be negative. Okay, fortunately, Dean also talked about equitable partitions, so I won't dwell too much on that. My goal will actually be how to factor this Töplitz matrix. So I'll just glance through these equitable partitions. Remember, these are the partitions where between two cells, when we look the induced graph by edges between two cells, we just say if these are red and blue cell, that every red vertex has the same number of blue neighbors, and this is it. And of course also vice versa, every blue neighbor has the same number of red neighbors, and these are constants, structural constants of this equitable partition. And yes, Dean already mentioned that such partitions come from orbits, but not necessary. Yeah, like this example where I took one skeleton of the dodecahedron and took the distance partition corresponding to an edge, and I found out again some equitable partition. Okay, now these equitable partitions are quite strong. Just observing these two objects, the dodecahedron and Peterson graph, we can do the distance partition corresponding to a vertex. So these are these blue circles. They consist of neighbors of this point, and then vertices at distance 2, 3, 4, and this one at the distance 5. And if we do such a partition, we can also make a quotient. So we take cells to be vertices, and we put arcs between cells corresponding to this constant Cij. And here's the example of this. Of course, because in the definition, the graphs induced by cells are also regular, We have also these CII constants. And so when we do this operation, then we can get some loops. So when we do the distance partition, then we get the weighted path with some loops. But we can do also some other equitable partitions we can find. For example, the diagonals join the antipodal vertices. So antipodal pairs of vertices form, they can also form the cells. And when we do the quotient in this case, so this time if there is an arc this way and this way, we'll just substitute it with an edge. We get Peterson graph. Okay, so thinking about eigenvalues, you can see that eigenvalues of the dodecahedron are all these numbers here together with multiplicities, but the red numbers are the eigenvalues of the Peterson graph, and they nicely interlace the eigenvalues of the dodecahedron. And we'll talk more about that later. Okay, so Dean was also talking about how to make a characteristic vector of some set, the support vector of the set. And we put all the support vectors of partition, we can build the P matrix, and then we have this characterization property that partition is equitable. If there exists such matrix B, so that AP is PB, or we could also say that the column space, the span of column space of these support vectors is A invariant. And of course, this B matrix is just the adjacency matrix of the quotient. Okay. Yeah, I could dwell, but I'm sure that you're all familiar what to do in this case with eigenvectors of the matrix. There are nice connections, and so if we have a eigenvector of the quotient, we can extend it to eigenvector of the original graph by putting the same constant on every vertex corresponding to cell C, and if we do this, then we have the multiplicity of the original of the eigenvalue in the original graph is at least as much as multiplicity in the quotient. And yeah, we can do some similar trick also by the eigenvalues that don't belong to the quotient. They actually, the only condition on the eigenvector is has to be non-zero, so that that means that if the eigenvector of the original graph is not the eigenvector of the quotient, that means that it has to sum to 0 on all the cells. Okay, what I also need, and I already mentioned this example of the dodecahedron and Peterson graph, is I need a special partition. So I'll define H to be R cover of graph gamma if we can partition H into independent sets. These independent sets are called fibers, and between any fiber I have either matching or nothing. And so of course then we can, this is also equitable partition because the fibers are independent sets, so they are regular, and between any two fibers we have these constants are equal either 1 on both sides or 0. So this means that this is equitable partition, and we can do, and actually graph below is actually the quotient. Now we can also geometrically interpret that we have a projection. You can imagine that you have a light that you put on top, and the shadow is in this graph below. Also locally, at every point, if you take the pre-image of a point which is called fiber, then the neighborhood of that looks the same. So the claw goes to several copies of claws. So if the shadow graph is k-regular, then the original graph, the covering graph, R cover, is also k-regular. because these clause live too close to R copies of clause. Okay, so this R is called the covering index, and we'll study special kinds of covers, and these are we'll study actually the antipodal graphs. What I need in the antipodal graph is that being, so suppose that we start with a graph of diameter d, and we need that being at a distance 0 or diameter of the graph is an equivalence relation. Now everything is trivial, but transitivity is non-trivial thing, non-trivial condition. So we have u and two vertices at a distance d from u, then they have to be at a distance d also between themselves. So we have this transitivity in the case of this dodecahedron. We only have one antipodal vertex, so there's nothing to check. So that is antipodal, but those were the pairs of antipodal vertices anyway. So we'll actually study antipodal covers. So the covers where fibers actually are consisting of antipodal classes, because this is equivalence relation. We have antipodal, we have equivalence classes, and we call them antipodal classes. And so the graph that is covered by these antipodal classes we'll call antipodal cover. And antipodal covers have a lot of structure. For example, Chris Gotsil mentioned that if L is smaller than D, the diameter, then when you try to live the cycle, it actually and this cycle is shorter than D, then it has to live to union of cycles. So for example, triangles live to triangles. So then graph not just locally like in the topological sense, but or also in the graph theoretical sense, the neighborhood graph is also then if diameter is at least 4, for example, then you already triangles live to triangles. Okay, so Töplitz matrices are, I promised that I'll factor the determinant of this Töplitz matrix. Now, Töplitz matrix has this property that these entries are constant. And so on, and we have we can put always, we can scale it so that we have one on diagonal, and we'll try to calculate as big determinant of Töplitz matrix as possible. So Töplitz, actually, I find out that he's a predecessor of my supervisor, so it's mine as well. So it's somehow some kind of a granddaddy. So great that I have a result. So although probably he showed it already, but anyway, so the gram matrix of when we represent the vertices of a geodetic path, it's actually a Töplitz matrix, and we can, in a sense, use exactly that, and together with equitable partitions. So I claim that this factorization consists of two smaller determinants, half of the size, about half of the size, unless the dimension of original matrix is odd, then one has to be m and the other one m+1. And this is how these smaller matrices are defined. And if in the odd case, you have to do a little bit more. Now, so how to go and prove something like that? Well, you can do equitable partition of the path, and then use the properties of this equitable partitions connection with characteristic polynomials and so on. So, I mean, it's kind of an easy exercise to show quickly the determinant of P divides the determinant of T, and now you do the same for the other factor, and you're kind of done. It's nice that eigenvalue techniques actually help us answer the questions which are kind of, it seem like very algebraic or solely algebraic. Okay, now the distance regular graphs. In a way, they're just a presentation of discrete orthogonal polynomials in some sense. And of course, I think Jack already talked about distance regular graphs. I don't need to define the distance regularity. He also mentioned that we have the intersection array. So these are these BIs and CIs, the constants, so that when we do a distance partition, when we go from I to I plus first sphere, then we have BI neighbors there. But if we go back to the I minus one sphere, minus first sphere, then we have these constant CIs. And of course, Jack also mentioned that while the distance regular graphs are regular graphs, and the number of neighbors sums, so if we take these bubbles to have valency AI, then the sum of these three numbers is equal to K. So we kind of don't record this. Okay, usually we put in these bubbles also the sizes, and these sizes can be calculated from BIs and CIs. Actually, it turns out that almost anything can be calculated from AIs, BIs and CIs, in particular eigenvalues. Now, these equitable partitions help us realize that all the eigenvalues of the graph are in this weighted path. And this weighted path can be recorded as a free diagonal matrix. And so when we try to calculate the eigenvalues of this tri-diagonal matrix, we'll actually get also the eigenvectors, and these eigenvectors will have a free-term recurrence relation, so they'll in turn be orthogonal polynomials. Okay, so in particular here, this example of Peterson line graph or Peterson graph is actually also antipodal, but the size of antipodal classes is more than 2. So in particular, when we start with V, also these two red vertices that are at a distance 3 from V, they also have to be pairwise at a distance 3. Okay, so yeah, Jack also mentioned that the distance regularity is consequence of the distance transitivity. So we'll skip this. All the intersection numbers, all the structural constants of association schemes can be calculated from these intersection numbers. And these intersection numbers have some nice properties. B is not decreasing, C is not non-decreasing sequence, and these sizes of these spheres are the unimodal sequence. And yeah, the simplest problems in distance regular graphs is to construct, given such an intersection array, to construct a graph or prove its uniqueness if the construction is already known, or to find out why that particular sequence, there is no graph that realizes this sequence. Okay, so polynomials I already mentioned. I'll dwell a little bit more on that, so that this is the tri-diagonal matrix which helps you calculate all the eigenvalues, because when I'll go now to antipodal graphs, it will turn out that we can calculate the intersection array from this quotient. But first, let me say that if we want to classify all distance regular graphs, one way of classifying these graphs is by determining what are the primitive graphs. These are the graphs where the distance graphs, so gamma 1 graph, gamma 2 graph when we join the vertices at distance 2, or gamma D graph when we join the vertices at distance D, that all these are connected. Now in antipodal case, gamma D is just union of cliques, And in bipartite case, we have two parts, so these graphs are then gamma 2 is not connected. So it turns out that if the graph is imprimitive in distance regular case, then it has to be either bipartite or antibodal, or actually both. This is Smith's theorem, and basically this is idea why we try to determine if primitive graphs have the graphs antibodal covers to kind of solve this classification. Now, if you want to classify, if you want to calculate, so if you want to figure out if some graph has a cover, then you have to determine what are the intersection array of this cover. And Gardner actually proved that, in short, that the diameter of a quotient is actually d over 2, where d is the diameter of the cover, and then gave the intersection arrays. And the intersection arrays look very similar, like the original intersection, like just kind of glued together B's and C's the other way around, and maybe something in the middle different. Maybe we can write this in the matrix form, but it turns out that this matrix actually breaks into two smaller matrices, so that you can, when you're calculating the eigenvalues, you can calculate the eigenvalues, well, kind of similar like these Töplitz matrices, that you determine the eigenvalues of the old eigenvalues, which are well, already known if you knew the quotient, and then the new eigenvalues. And of course, it's a little bit different in odd and even case. Yeah, all this structure comes from this, how the paths are being lifted. And we actually, for every antibodal graph, we have such a picture depending on what's the size of the fiber. Okay, so I won't dwell on the eigenvalues, but I'll say that once you study these covers, you find out many combinatorial objects, like two graphs, projective and affine planes, Hadamard matrices, more graphs, and even more general structures. Okay, because I have 15 more minutes, I'll give you now the application of another application. Well, actually, we used orthogonal polynomials to kind of get a faster arithmetics on elliptic curves. Now we'll try to use elliptic curves to solve some problem in algebraic combinatorics. And when I was studying non-bipartite antibodal distance regular graphs, so the ones that are imprimitive of diameter 4, you could study, for example, the Krein parameter, and if this Krein parameter 444 in this case turns out to be 0, then it seems like that there is some kind of a classification in order. Now, either this quotient is triangle free and also strongly regular because it's half of the diameter. So in this case, the classification will be difficult because we don't know many strong triangle-free strongly regular graphs. Or we'll have some family of antibodal tied graphs that I won't go into that. Or we have 3 and 4, and these 3 and 4 conditions seem to never be realized by any numbers. We couldn't find any numbers. But I noticed that in this second case, what we get based on study of eigenvalues is that the antibodal quotient is actually the point graph of generalized quadrangle W and W square. And I think Cameron, Hutels, and Seidel proved that if the graph has such parameters, then it has to be geometric, and the maximal cliques actually form of the graph form the lines, and so you really get to play with geometry. And so the question was, if you turn around, if you start with generous quadrangle and then form a strong irregular graph out of it, does such a strong irregular graph has a cover or not? And well, if there is a cover, then based on study of eigenvalues, it turns out that this has to be perfect square because of the integrality of multiplicities, and then as a consequence also integralities of eigenvalues in this case. So I recognize, of course, that this is elliptic curve, and I conjectured that this elliptic curve doesn't have any solution. Of course, it does have one solution. If you take W to be 0, then you get Y to be plus minus 1. So there are two solutions, but if you assume that W is not positive, then I suspected that there are no solutions. I thought, well, the theory of elliptic curves will just tell me that. Now, studying this problem, I can tell you that Brouwer and Van Boon already proved that this relation of antipodal cover of point graph of generous quadrangle cannot happen for W being a prime power. But in general, we didn't know. Now, elliptic curves were really thoroughly studied already till 1920. There were these four mathematicians, Cauchy, Lucas, Sylvester, and Poincaré, famous mathematicians who were dealing with elliptic curves. But after that, this just exploded. So they say that it's not a thread that you could speak about elliptic curves hours and hours. But in 1985, elliptic curves were used by Leenstra to factor the integers for primality testing. And as I already mentioned, Neil Töplitz and Victor Miller were proposing for the group where you would do the exponentiation. So I thought I would need to use all this theory, but anyway, I gave this problem to my student, Matthias Schurlep. So I said, well, consider this elliptic curve and prove that there are no solutions, but those trivial ones that I just mentioned. Well, he first proved that there are no solutions, but the proof was wrong. But then found out an elementary way to convince me that there are no solutions. So he was just considering this mod 16, and in this theorem there was also information that this T, which is W minus 1, is even, which means that W is odd. So we put the W is odd plus 1 in this equation, and we multiply and look modulo 16, we get either 8 or 12. Well, but there are no perfect squares modulo 16 of this form, because when you square the numbers, you will get only this 0, 1, 4, and 9. So, well, there is no intersection between these two sets, and there is no solutions. So this item 3 is, we can forget about this one. For the fourth one, I suspect it will be a little bit harder, because you get a polynomial that is variable of two variable polynomial of degree 6. So no use of elliptic curves. Still, in distance regular graphs, we often study cubics. So keep in mind that there might be a way to use elliptic curves as well, and based on just this example. Okay, I have 7 minutes, so I can go through my favorite open problems. I'll basically deal with distance regular graphs of small diameter. Some will be connected to codes, and there is also this classification of 84 family, but maybe I won't go into that because the questions there were already published. Okay, so the first intersection array that we would like to solve is this very neat intersection array. If you just remember the parameters that Dean was mentioning, that they were higher degree polynomials, but here everything's kind of linear, and the CIs are just 1, 6, and 28. So how difficult could that be? If you go and calculate the number of vertices, it turns out to be the cubic. So it seems like a nice graph. Actually, this family was already mentioned in BCN, our Bible for distance regular graphs, and was mentioned that it's also formally self-dual, and also it has classical parameters. So I tried to see what we can do about this family. Now the you can build examples from bilinear forms graphs when R is power of 2, and so then I don't know but for example, if you take 2 to the third, so R is equal to 8. You have this example, but uniqueness is not known. So uniqueness is still open for such a small graph, which is amazing. But since we have a smaller one, let's see what is with R is equal 6, which is a composite a product of 2 primes. And it turned out that another student of mine, Janusz Vidali, who already finished, and me proved that this graph doesn't exist, and the proof actually depended on theta being so the second eigenvalue being equal to -1, or with other words, that there are some kind of perfect codes there, and these perfect codes and the structure actually reminds us of these antipodal graphs, and when we used all this, we proved non-existence. Actually, Vidali, this was for some time Vidali's PhD problem, so he proved all kind of structural things, that these graphs cannot be locally grid graphs when R is 7 or 3 divides R, and so on. But soon, once we talked with Misha Musicuk, we realized that that's actually a more general family. So these numbers 1, 6, and 28, while they can be described as n times n plus 1, and this a little bit harder product, and yeah, also these are formally self-dual and classical, and also this one have examples from bilinear forms. The number of vertices is still cubic. Actually, Musicuk proposed a construction, and Janusz proved that that's actually equivalent to bilinear forms graphs. But still, uniqueness, it is known by Cypers, so some Dutch mathematician, that for very large R, this need to be bilinear forms, but for small ones, this is still open problem. So, okay, let me move to problem C. Now here, this is amazing graph on 585 vertices of diameter 3. So kind of the same as these 2 graphs before. Now, this is also the member of infinite family of graphs, and it turns out to be cube polynomial. So we have vanishing of prime parameters. Based on that, we can go and calculate triple intersection numbers in some cases. And what we find out is that the third subconstituents of this graph is actually antipodal covered. And actually, we proved that there are some perfect one codes in this graph. But this is really neat, that actually the third subconstituents is antipodal distance regular graph. So I went to the table of antipodal distance regular graphs and tried to find out if this graph on 84 vertices is known. Unfortunately, it's the smallest open case, so we couldn't get anything there. But considering the local graph, it turns out that the local graph is union of, well, not union, but it forms a equitable partition of 4 20s. And we were able to prove, and all the parameters here are 4, 4, 4, 4 all over the place. And you can show by interlacing techniques that that this 20 graph is actually connected, and I don't know. It seems like that it's difficult to construct such a graph on 80 vertices, which with so much structure. But so far we didn't succeed yet. But we were able to prove, for example, that these maximal one codes of size 5, they're actually completely irregular codes and give us more of equitable partitions like this one, 5 plus 400 plus 180, and the equitable partition is outlined here. Now going to this 84 distance regular cover, here are the parameters and eigenvalues, and this is the distance partition corresponding to one fiber of antipodal class. And it turns out that this 20 graph appears there as well. It's actually the local graph, so it is connected. And this 20 graph of valency 4, what could it be? We actually find out all the information on eigenvalues and try to determine that. But I'll actually stop here because my time is up, and I think this is good enough challenge for just about anybody. Thank you for your attention.
Thank you, Sasha. Thank you very much for your talk. But it looks like your philosophy of mathematics, and thank you very much for showing us relationships between modern mathematics and classical ones. Thank you very much. So, are there any questions to the speaker?
Yeah, I have comments.
Yeah, please, Sasha.
So, Sasha, can you show, please, the slide about bilinear forms graphs?
Yes. This one. Yeah, the general one. If you take here.
No, the
previous one.
Yes, page.
The previous one. Yeah. So I think that the uniqueness of this. So when R equals 8, it is the bilinear forms graph over the binary field, right?
Yes.
Yeah, I think that its uniqueness was shown by Jack and myself, so it's unique.
Oh, okay. Okay, good. Excellent. I'll check.
So,
and you also mentioned, so you also mentioned in the next slides.
Yes.
Yeah, so I guess Match, so he's German mathematician, so he showed that bilinear forms graphs are unique for many, for almost all actually parameters. So there is
from somewhere on, but not for small one.
Yeah.
So they need to be big enough. Yeah. I think Cyprus was a mistake. It was actually Match. Yes, you're right.